Excellent. And the mic is yours. You can start whenever you're ready.
Thank you very much. Should I share the screen again?
I think we are seeing the screen right now.
Okay, you see it. All right.
Yes. Excellent.
So what I'm going to talk about is almost all of it is on the archive, except for this third preprint, which is still being improved. So just one little result will be slightly new. Okay, so for today, I'm going to call by a link a topological link. That is an injective continuous map from a disjoint union of circles into S3. And two links are called isotopic if they are homotopic through links. So this is topological isotopy, and it can be a little bit unexpected that every piecewise linear knot is isotopic to the unknot in this sense. And here is a picture for the trefoil. You can imagine that you tie it on a rope, and then you pull the rope in the opposite directions so that the trefoil becomes smaller and smaller and eventually goes to a point. It's not that you collapse it together with the space which surrounds it. You pull the rope so that less and less of rope goes into this trefoil, and then you have just one point, and all of this is legal. You don't have any double points. It's injective. It's contiguous. So you can kill every knot by an isotopy. Actually, if you do it carefully, it's a conical process, so it's a piecewise linear isotopy. Okay, and there is the following proposition proved by Rolfsen: two piecewise linear links are PL isotopic if and only if they are related by the equivalent relation generated by ambient isotopy and insertion of local knots. So here is a picture from a paper of Rolfsen of how it can look like. There is some knot appears and some knot disappears in this picture. And Rolfsen asked the following problem: if two piecewise linear links are connected by topological isotopy, are they always PL isotopic? So I will study this for links in the three sphere. It's not clear if commands a three sphere or an arbitrary three manifold. The first theorem says that the answer is affirmative if the following conjecture holds. Namely, piecewise linear links in S3 are separated by finite type invariants. This is just a little extension of a well-known conjecture by Vasiliev, which says that piecewise linear knots in the three sphere are separated by finite type invariants. Some people mention this more general conjecture and even some stronger conjectures in their papers, but let me not go into that. Now, you may say that, okay, so one conjecture follows from another conjecture. Is there any, so to say, constructive theorem? Yes, there is a constructive theorem. Namely, if you have piecewise linear links connected by topological isotopy, then they are PL isotopic to another pair of links, which are not distinguishable from each other by finite type invariants. And then some people might say that finite type invariants are interesting, but topological isotopy is not interesting. It depends on taste. And I have a theorem for those people as well. Namely, it says that this version for links of the Vasiliev conjecture holds if and only if 6 other conjectures hold simultaneously, namely the original Vasiliev conjecture for knots, the affirmative answer to Rolfsen's problem. This is the second one. Now this is the third conjecture, which will be in this list. So it is more or less what was stated by Haberger and Melikhov in their paper, except that they didn't say it very precisely, and there are several ways to interpret what they stated. So one of these ways is as follows. If two piecewise linear links in S3 are not separated by finite type invariants, then for each n, they are not separated by type n invariants of string links. So what do I mean by that? I say that two links in S3 are not separated by a class C of invariants of string links, so closed links are not separated by a class of invariants of string links. If they are equivalent with respect to the equivalence relation generated by ambient isotopy and the relation to B closures of string links that are not separated by invariants of that class. So it must be not very easy to understand what exactly is going on here. And in my paper, I have some examples to explain what this means with triple mu invariants and some other invariants. But let me not go into that now. Somehow we have to, because this conjecture of Haberger and Melikhov is unsolved, we have to, or maybe for other reasons, but somehow we have to resort to string links. And the theorem says the Vasiliev conjecture for links is equivalent to the conjunction of the following 6 conjectures. The Vasiliev version for knots, the Haberger-Melikhov conjecture, and the 4 conjectures which assert that the following 4 implications can be reversed for any PL links L and L prime and S3. So the 4 implications are as follows. We start with saying that L and L prime are PL isotopic. This trivially implies that they are topological isotopic. Now this also implies, and this is not trivial, this is a theorem, that L and L prime are n quasi-isotopic for all finite n. Now, what is n quasi-isotopy? I'll tell you soon. Then there is another theorem which says that this implies that for each n, L and L prime are not separated by colored type n invariants of string links well defined up to PL isotopic. So here I have to say what is colored type n invariance, and I also have to say that here we are speaking about closed links not being separated by invariants of string links. This is in the sense of the definition from the previous page. And then there is a trivial implication from the previous assertion to the same assertion, but without the word colored. And this is a trivial implication. So when you the converse assertion to each of these 4 arrows is a conjecture, and if you take these 4 conjectures and those previous ones which I mentioned, they are going to be equivalent to Vasiliev's conjecture for links. It sounds a bit complicated, but let me tell you the definitions, and then there will be a simpler version of this theorem which doesn't mention string links. Actually, if you do rational finite type invariant, then you don't have to deal with string links. So I have to define colored finite type invariant. This is something which was defined by Kirk and Livingston in their 1998 paper, but they didn't use the word colored. So we start from an invariant V, of piecewise linear links or string links. We extend it in the usual way to singular links. I hope everyone is familiar with this. So the V is defined on links with no double points, and then when we add double point, a double point, we have this formula to define the extension inductively. Then V is said to be of type n if its extension vanishes on singular links with n+1 double points, or with at least n+1 double points, it's clear. And this is something everybody knows. And V is said to be of color type n if its extension vanishes on those singular links with n+1 double points, whose all double points are self-intersections of components and not intersections of distinct components. So we look only at self-intersections of components, and we count those self-intersections, and we don't care about intersections between distinct components when we define this colored type. So colored type n invariants are related to self-CN equivalence in the same way as usual type n invariants are related to CN equivalence. At least in the easy direction. So colored type n invariants agree on any two PL links or string links which are related by self-CN equivalence. This is a very easy proposition. And in the reverse direction, it is something can be said, but it's a long story. So one reason why colored type invariants are interesting is that there are much more of them than usual type n invariants. And in fact, there is a following unsolved conjecture of Kirk and Livingston. The conjecture is that there exists an infinite family of linearly independent Z-value colored type 2 invariants of two-component PL links with linking number 0. So this is something that cannot happen for usual finite type invariants. And there are, I understand why they conjecture that. There is a lot of geometric evidence for this conjecture, but it remains unproved and also not refuted. Now, I also have to say what is n quasi-isotopic. So it's a geometric equivalence relation on links or on string links, and in general, we can consider embeddings of one manifold, proper embeddings of one manifold in a three manifold. And two such embeddings are called n quasi-isotopic if they are connected by a PL homotopy through embeddings and n quasi-embeddings, which I have to define. So maybe I should have said there that we consider only generic piecewise linear homotopies, which have just isolated double points which occur by one at a moment. And so we look at a piecewise linear map. It can be a link or a string link or maybe something else, which has a singular link with one double point or a singular string link with one double point. So it has precisely one double point, and we call it an n quasi-embedding if the following holds. Namely, if in addition to this double point, which we call P0, there exist compact polyhedra P1 through Pn in the range, in the three manifold, and also arcs J0 through Jn in the domain, in the circles or in the strings, such that the preimage of the ith polyhedron lies in the ith arc, and for each I. And also the image of the ith arc lies in the polyhedron Pi plus 1. And also the polyhedron Pi lies in pi+1. And finally, the inclusion of both of them in pi+1 must be null-homotopic. So that condition, that last condition, certainly holds if each pi is contractible. So as a simplified version of this definition, you can imagine that instead of the final condition, there is a requirement that each pi be contractible. So you have arcs in the domain and contractible polyhedra in the range. And then, well, we'll see an example. So here is the Milnor's link. So the picture shows M4, and in the same way you can have MM. So I claim that it is n-1 quasi-isotopic to the unlink. And it is known that it is not n quasi-isotopic to the unlink. This was shown using Cochran's derived invariance and Milnor's bar mu invariance. There are several proofs of this fact. So how to see that it is n-1 quasi-isotopic to the unlink? Well, let us make just one crossing change. If we do this intersection here, then we get another link which is easily seen to be unlinked. So we unlink our link by making this one crossing change. And so it's enough to look at this intermediate singular link with one double point and to show that it is a 3 quasi-invariant. If we want to show that Milnor's link M4 is 3 quasi-isotopic to the trivial. So we already have our polyhedron P0, which has to be this double point by the definition. And now we need to find an arc J0, which contains the preimage of P0. Well, we can take the minimal arc with this property, and its image will be a loop, like shown in the picture. Then we need to find the polyhedron P1, which contains this loop, and also such that this loop is contractible. Well, we can just take a disk spanned by this loop. Then this disk is going to intersect the link again. We cannot choose a disk which will not intersect the link. So at the next step, we need to find an arc J1, which contains the preimage of P1. So it must contain both this green arc and this new point of intersection. So the minimal arc with this property, well, okay, one of two minimal arcs with this property is this arc which is shown consisting of the light green part and the dark green part. So it grows. PI's grow and JI's grow. All right, we have this arc J1, and now we want to find the polyhedron P2 such that the image of this arc and also the polyhedron P1 taken together are null homotopic. Are null homotopic in this P2. We can do that. Namely, here is this polyhedron, so it's no longer a manifold with boundary. It's really a polyhedron, or you can take it's a collapsible polyhedron, so you can take a regular neighborhood of it and you'll get just a ball. So you can do both if you prefer. But no matter how you choose it, well, it's, at least here you can see that it intersects the link again, and so this process is going to continue in the same fashion until you get to a point when if you want to choose a next polyhedron, it is going to intersect the other component of the link. And this is not good because its preimage will then contain points on both components. And we must have the preimage contained in the arc and this arc cannot contain points from two different components. So here we have to stop, but we have found three P0, P1, P2, and P3, and also these arcs J0 to J3. So this singular link is 3 quasi-embedding, and so Milnor's link M4 is 3 quasi-asymptotic to Dunning. Here is another example where this definition works differently. This is the iterated Whitehead link, namely W3, and I claim that actually Wn is then quasi-asymptotic to the unlink. Well, here we can again make this crossing and get a link which is easily seen to be unlinked. So it's enough to look at this singular link. We have P0, then we can find the minimal arc J0, which contains a preimage of P0. And then, well, instead of drawing this disk, let me do something different. Let me draw the solid torus, which is disjoint from the green component and almost contains the entire blue component, except for a small arc. So I leave a small arc out of it because I want to have arcs in my definition, and so this is why I'm leaving this small arc. So now this is P1, and if you look from a distance at this picture, you see that this is a Whitehead link essentially. So if you think of this red solid torus as a knot, as the unknot, but the Whitehead link is symmetric. So let me redraw this picture in an equivalent way. Well, okay. So before I do that, I can draw the arc J1, which subsumes all the blue component except for this arc which we left outside. Yes, and now let me redraw this picture in an equivalent way. The green component became simple, and the red solid torus became Whitehead curve. And we still have this blue arc and this remaining part of the link, which I didn't draw in detail. Now we want to find the next polyhedron, P2. And we can do that. We just take the solid torus, which is disjoint from the blue component, and contains this red solid torus, and this blue arc still stays outside. And for the next arc, J2, we can take the same as before. We can take the J1. And so this is actually what we wanted, to show that W3 is 2 quasi-asymptotic to the unlink. This is precisely all that we needed. And in the same way, you can show that iterated Whitehead link Wn is then -1 quasi-asymptotic to the unlink, but it needed to be untwisted because the symmetry of the Whitehead link works only for the untwisted Whitehead link, left-handed or right-handed. Now, somehow I was unable to prove that Wn is not n quasi-asymptotic to the unlink. Thirdly, it is not possible to do this using the Alexandria polynomial or the convex tensor function. I suspect that this can be done using colored Jones polynomial, but this nobody has done it. So let me go back to the statement. So now this is a new version of theorem A, and it says that for any PL links L and L prime and S3, there are the following implications. The first implication is trivial again. If L and L prime are PL isotopic and they're topological isotopic, then the theorem says that if they are topologically isotopic, then they are n quasi-isotopic for all finite n. This is the point of this equivalence relation of n quasi-isotopic. Another point of this equivalence relation is that if they are n quasi-isotopic, then they are not separated by type n invariants, and even by color type n invariants, which are well defined up to PL isotopic. So not by all of them, but only by those which are well defined up to PL isotopic. And then again, you can omit the word colored, and you get a trivial implication because finite type invariants are colored finite type. So there are these four implications, and all of them can be reversed at the same time if and only if the composite implication from top to bottom can be reversed. And the composite implication reads as follows. It says that PL isotopic classes of links in S3 are separated by those finite type invariants that are well defined up to PL isotopic. So this can be considered as a version of the Vassiliev conjecture for links modular nodes, because it's modular local nodes. PL isotopy is addition and insertion of local nodes. And you might ask how this Vassiliev conjecture for links modular nodes is related to the original Vassiliev conjecture. The answer is it can almost be shown to be equivalent to. I can almost show that the Vassiliev conjecture for links is equivalent to the conjunction of the Vassiliev conjecture for nodes and the Vassiliev conjecture for links model. Almost means that this works if rationally, if you consider only rational finite type invariants. And also this works for string links. For closed links, there is no proof, it's an open problem. So if you believe in this equivalence for closed links, then this theorem A can be stated much easier without using string links. All right, so let me mention a few words about the proof. One ingredient of the proof is the following theorem B. Every string link admits a unique decomposition into a connected sum of its prime local nodes and a string link which has no local nodes. It's not very accurate, but I think the meaning is clear. So it would seem that this is a trivial theorem, because it's well known that every non-split link admits a unique decomposition into prime links. Unfortunately, it doesn't easily follow from that classic result, because there is the following example. There is a string link which has no local nodes, but its closure has a local. So this string link is in the middle here, and its closure is on the right, and you can see that this closure indeed has no local. This closure has a local node because you can remove this green component, just pull it along the blue component, and you get a local node. And it's possible to prove that the original string link doesn't have local node if you consider a non-standard closure, which is shown on the left. So in this non-standard closure, it can be proved using the Jones polynomial that this link doesn't have local. And to prove theorem B, I actually need to reprove Hashigumi's theorem about prime links. Okay, so now byproduct of the proof of these results is the following theorem. If we have a finite type invariant, which is invariant under PL isotopic, then it assumes the same value on all sufficiently close approximations of any given topological link. So we can extend it to topological links, so to say, by continuity. We just take any sufficiently close approximation, piecewise linear approximation, and evaluate it on this PL link. And this extension to logical links is going to be an invariant of isotopy. This is actually a consequence of the previous assertion, but anyhow, it's true. And also, you don't have to have a finite type invariant. It's enough if you have a colored finite type invariant, which is invariant under PL isotopy. So here are some examples. Let us consider a PL link. Let us divide its Conway polynomial by the Conway polynomials of its components. This quotient is a formal power series whose coefficients are finite type invariant. Also, this quotient is invariant under PL isotopy, because if you insert a local knot, both the numerator and the denominator will be multiplied by the same factor, namely by the Conway polynomial of this local knot which you insert. So every coefficient of this formal power series works for this theorem. But when you extend this power series, you get a formal power series, which is an invariant of isotopy of topological links. But it doesn't have to be a rational power series any longer, because you extend each coefficient individually. So if somehow you have a wild link for which this extended power series is not rational, then you know that this wild link is not isotopic to any PL group. And this is what we are going to use. You can also do the same for the Kontsevich integral. Let me not go into details. And you can also do the same for the Homfley polynomial, by the Homfley polynomial of the link, by the Homfley polynomial of the components, except that you have to take an appropriate power series expansion so that you get finite type invariants in the numerator and in the denominator. And you can do the same for the Kaufman polynomial. And you can do the same for the Conway potential function. But unfortunately, I wasn't able to apply this invariance, and instead I have to do something slightly different. Namely, I have to use a two-variable Conway polynomial, which is the following thing. We start with the Conway potential function for a knot. It is expressible in terms of x minus x inverse, and you get the Conway polynomial. For a two-component link or a link of more components, this is no longer true, but you can still do something of this type. You can decompose this Conway potential function, so to speak, in a symmetric part and alternating or skew symmetric part. So namely, you consider this Conway variable x minus x inverse, and also you consider the variable x plus x inverse. And also the same for y minus y inverse and y plus y inverse. And it's easy to see that you can expand, you can write this Conway potential function of two variables as a polynomial in u, v, u bar, and v bar. And actually, u bar and v bar, you don't have to use squares, cubes, and so on. It's enough to use just linear terms, because u bar squared equals u plus 4. So you can simply exclude all the squares. So this is a rather trivial observation, but less trivial observation is that if you just take the sum of these two polynomials P and Q. So these are now polynomials with integer coefficients. And you get that you had some factor here. You just get it and you add them. You get a polynomial in U and V, which is going to contain the same information as the Conway potential function. And U and V are sort of Conway variables. So you can call it a two-variable Conway polynomial. Its coefficients are no longer finite type invariants, but they are colored finite type invariants because Conway's first relation translates well into these terms, and it is going to tell you precisely that. Of course, if you substitute the same variable for both U and V, you get the Conway polynomial. So now, if we divide this two-variable Conway polynomial by the Conway polynomials of the components, we are going to get, like before, a formal power series in two variables, which extends to an invariant of isotopy of topological links, and it is invariant under sufficiently closed approximation. But for each coefficient, generally speaking, you have its own epsilon. It turns out that you can say more. You can decompose this two-variable Conway polynomial. If you write it as a power series in U, coefficients are power series in V, then each of these coefficients, which is a whole power series in V, is going to be invariant under sufficiently close approximation of the first component. So it means it has the same epsilon for the first component. You have to tell just one epsilon, and then for every PL link, which is epsilon close to our given topological link, this power series will be the same. It is epsilon close on the first component, and on the second, there are different epsilons. All right, so this is the ingredients which I need, and now I can talk about wild links. Oh no, I need one more ingredient. If we look at this power series, the first one, R0, is just a function of the linking number. The second one is essentially the generating function of Cochrane's derived invariance when the linking number is 0. So this is essentially a theorem of Biotek team, and well, he proved it for the Alexandria polynomial, so it was up to a sign. You can determine this sign, and also I have an alternative proof using the Seifert matrices. Now, for the purposes of topological isotopy, the more interesting case is when the linking number equals 1. And in this case, there is a geometric description of the same power series, R1, in terms of similarly defined invariants, so to say, Cochrane's generalized invariants. And to get that description, you need to find Seifert surfaces for the two components which intersect transversely in a single cluster. And it's always possible to do that by a result of Amundsen, Anderson, Davis, and Blair. It's an easy lemma. And then we fix also, in addition to the Seifert surfaces, we fix also a symplectic basis for the first Seifert surface, which is withdrawn from the class. And then we just evaluate this generalized Cochrane invariance of this on this symplectic basis, and this gives us a geometric description of the coefficients of this power series. Yeah, so these generalized Cochrane's invariants are defined using iterated intersection of Seifert surfaces like the original Cochrane's invariants. And when P equals Q, they were studied by Gilmer Livingston, and when L equals 0, they were also studied by Tsukamoto and Yasupara. And in fact, they determined all of them. So you can call this Tsukamoto-Yasupara invariance, or different version of that. Okay, so finally, we come to the second problem of Rosen. Is every knot isotopic to a piecewise linear knot, or equivalent to the unknot? In particular, is the Binks link isotopic to a PL knot? The Binks link is the following wild link constructed by Bink. It's an intersection of a nested sequence of solid tori. So you see a big solid torus. Inside of it, there is a knot, and then there is a smaller solid torus, which is a regular neighborhood of this knot. Then inside of this smaller torus, you have a very similar picture with more periods. And then you take a regular neighborhood of that knot, which is a still smaller solid torus. And then you keep going, and you take the intersection of all those solid tori. If you do this well enough, namely if the cylinders are small enough, then this intersection will be homeomorphic to S1. And there is a wild mode constructed by Brain, which is locally at every point exactly the same as the Binks link, but it is isotopic to the unknot. It's sort of a spiral construction, but let me not go into details. Some time ago, I proved that not every link is isotopic to a piecewise linear link. So now there is the following theorem. Let us start from the Binks link, and let us insert any PL knot in the complement to the Binks link, so that it has linking number 1 with the Binks. Then this pair, this two-component link, is not isotopic to any PL link. So I cannot show that the Binks link itself is not isotopic to a PL knot, but I can do that if you manage to insert a PL knot which links it with linking number 1 and keep it through the isotopy, also by an isotopy. Okay, so it doesn't actually have to be a PL knot, the one which you insert. It can be wild. So the version of theorem 2 says that the Binks link is not isotopic to any PL knot by an isotopy extending to an isotopy of two-component links with linking number 1. So here, this second component can be wild as well. So for example, this two-component link shown here, consisting of the Binks link and of this PL knot Q, is not isotopic to the same link, but with the components interchanged. Or you can take any other link instead of Q, even any other knot instead of Q, even wild, in the complement to the Binks link. So here theorem 2 is proved using just this reduced conway polynomial, the conway polynomial divided by the conway polynomial of the components. And here theorem 2 prime uses the two-variable conway polynomial divided by the conway polynomial of the component. Do I still have some time?
Just 2 minutes left, but I guess it's okay.
Okay, so let me tell a bit more then. The question arises immediately: does every isotopy of knots extend to an isotopy of two-component links with link number 1? So if this is true, then Rolson's problem would be solved, because by just using the previous theorem, we solved it. Unfortunately, the answer, which was not long ago obtained by Andreas Zastrov, is no. And actually, there exists an isotopy from the unknot to itself, which does not extend to any isotopy of two-component links with linking number 1. Even if you allow to self-intersections for the additional components, it's still not possible to extend it in this way. So it doesn't extend to even to a link homotopy of component links with linking number 1. However, you can devise still weaker equivalence relations than link homotopy. So link homotopy is very weak, but you can do still weaker. And there is an boardism, which I'll define in a moment, such that every isotopy of knots, topological isotopy of wild knots, extends to a two-boardism of two-component links with link number 1, even if you specify the initial link and the final one. So what is n-boardism? Now we allow the additional component not only to self-intersect, but also to get replaced by new additional component at any moment, at any instant of time, as long as it remains disjoint from the original component, the one which we had originally in our isotopic at this time instant, and also as long as it remains in the same conjugacy class modulo the nth derived subgroup. Here is the quotient of the fundamental group of the complement to the original component, that is time instant t. So the derived series of a group is something I guess everyone knows, but here I'm using also the half integer ones, which are defined in a similar way. And then another version of theorem 2 says that the Binks link is not isotopic to any PL knot by an isotopy extending to a 2.5 boardism of two-component links with linking number 1. If you are not happy with half integer derived series, you can replace 2.5 by 3 or 4. Any integer greater than 2.5, it will be still a true theorem. And this theorem requires this geometric description of the coefficients of some of the coefficients of the reduced two-variable convex polynomial, which we had a few slides ago. So here in the previous theorem we have two boardism, and here we have 2.5 boardism. If this were the same number, then again Rolfson's problem would be solved just as a consequence of these two theorems. But unfortunately, these two numbers are different. And so one can ask, okay, can one put 2.5 in this theorem here? Unfortunately, the answer is no. There exists an isotopy from the unknot to itself, which does not extend to a 0.5 boardism of two-component links with link number 1. And here is this isotopy from the unknot to itself. You take this wild link drawn in the picture and two meridians of it, and then for each meridional disk, you can push the remaining part of the link away from this disk until it shrinks to a point, in the same way as the isotopy that we had on the first slide. And this gives you an isotopy to the unknot. But you can do it for this meridional disk and also for this meridional disk, which gives you two isotopies to the unknot. When you combine them, you get an isotopy from the unknot to itself, and it turns out that it doesn't extend to an isotope even to a 2.5 boardism of two-component links with link number. So Rolfson's problem is not solved, and maybe this is a good place to stop. Thank you very much.